Good morning, class. Yesterday we looked at the formula for determination of surface area of solid objects, which we call prisms. Today we want to continue with further examples on the same, and we have an exercise just on composite objects. We want to see how we can still use the formula we derived for calculating the surface area of plane objects to calculate the surface area of these figures. So on the board we have an exercise of this particular object. We have opened its net, and we are now able to use the formula for calculating the surface area of various planes to determine the total surface area of this particular object. So this particular object is made of two quadrant surfaces, side surfaces, ADE and BCE. Those are quadrants. And as you remember, in our previous lessons, we had developed the formula for calculating the area of a quadrant. And a quadrant is basically a quarter of a circle. So that means we get the area of a circle and we divide by 4. And because they are two such similar, quadrants, we multiply by 2. The radius of those quadrants are 5 meters each. So we come and substitute, because this figure is made of rectangular planes and quadrants. We are now from the net. You can see that we have two rectangles whose dimensions are 10 meters by 5 meters. And another one also 10 meters by 5 meters. So because there are two of such similar rectangles, we can now be able to use the formula for finding the area of a rectangle to calculate the area of the two planes in the figure, and then we multiply by 2. So by substitution, we obtain So we obtain 2 into 22 over 7 times 5 over 4 plus 2 into 10 times 5, of which by simplification we'll get the following. From your calculator, you just get so you obtain the total surface area of this particular object as 139.28 meters square. And we remember we have said that it's very easy to calculate the surface area of an object by first of all opening the net. Once you open the net, it is very easy to use the formula for calculating various plane surfaces to calculate the surface area of the object given. So let's look at another exercise. So class, in this particular example, we have a cylinder, a solid cylinder, of which a quarter of it has been chopped off or removed. So in fact, we have what we call 3/4 of a cylinder because part of it has been removed, a quarter. And therefore, to get the surface area of that cylinder, we open and have its net. This is a sketch of the net of this particular 3/4 cylinder. And with the formula we've learned in the calculation of area of quadrants, semicircles, and 3/4 of circles, we are able to calculate the base and top areas of the cylinder and then the curved surface of that cylinder. So by that, from the information we have from the net, we can now appreciate that the area of the 3/4 of the two circles are 2 into 3/4 multiplied by pi r squared, where pi r squared is the area of the circle, 3/4 is 3/4 of the circle, and then because they are 2, we multiply by 2. That's why this 2 is outside the bracket. Then plus the area of the curved surface. And because the curved surface is 3/4 of the total curved surface area, we multiply by 3/4. It is 2 pi r h, because this is the formula we derived yesterday for the calculation of the surface area or curved surface area of a cylinder. So you multiply by 3/4 to get the curved surface area of that particular cylinder. So when we do the substitution, we obtain 2 into 3/4 times 22/7. The radius is 1. So it is 1 times 1, that was r squared, plus 3/4 into 2 times 22/7 times 1, which is the radius, times 4, which is the height or length of that particular cylinder. Upon simplification, we obtain 4.71. If you use your calculator to simplify the first part, you obtain 4.71 plus simplification by the calculator gives us the second part as 18.86. When you add the two, you obtain 23.56 meters square as the surface area of this particular object. And that one brings us to the end of the calculation of surface areas of objects. Today we want to move on and look at the volume of prisms and other three-dimensional figures. So class, we have dealt with various prisms. Yesterday I gave you examples of prisms that we have in life, and as such, when we look at prisms, we look at prisms in terms of surface area, which we have already done, and we look at prisms in terms of volume. Volume, in this case, is defined as the total space occupied by an object is known as volume. And therefore, when we discuss volume, we look at the three-dimensional measurements that that figure will occupy. For example, we can ask ourselves, what is the volume of this particular container, which is is defined by length, we have its width, and we have its height. So when we look at that particular object, we look at the three dimensions of measurements in that particular object, which defines length, width, and then height. And that is, such a figure is known as a cuboid. So we want to look at examples of three-dimensional figures and the formula for calculating their volume. And volume is basically multiplication of the three dimensions that we have in that particular object. So we multiply length, we multiply width, and we multiply height. So let's start with the first prism. We have a cuboid. And for a cuboid, we have the dimensions, length, width, and height. And we have said that for the calculation of the volume of a cuboid, we just basically multiply length by width by height, and that will be the volume of a cuboid. So we have the dimensions. We have the dimensions. We have the dimensions of the cuboid as 5 meters as length, 2.5 meters as width, and 4 meters as height. So So we get the volume of the cuboid as 50.0 meters cubed. 5 times 2.5 times 4 times 2.5 is 10. 10 times 5 is 50. So we get the volume as 50 meters cubed. Let's go to the next prism, next simple prism. For a cube, this is a figure in which all the edges are equal. So we'll indicate with the mathematical connotations. We indicate with the mathematical connotations that if all the edges are equal, the symbols we include in the figure are those. So you can see that here we have said that we have length, we have width which is also equal to length, and we have height which is also equal to length. So using the basic notation of the calculation of the volume over a prism, we get volume is equal to length times width times height. That is our basic connotation that we have in the calculation of the volume of a prism. So this is from this particular basic connotation, we can now see that we have length, which is this, but our width is equal to length, and our height also is equal to length. So where there are width, we substitute with length, and where there is height, we substitute also with L. So this implies that for a cube, we get volume as length times length times length. Volume is length times length times length. But because we have the same multiplication of the same variable, we multiply length times length times length, we get length cubed. Volume of a cube is length cubed. So if we know the dimensions, one side of the dimensions of a cube, then we can easily calculate its volume. Let's look at an example. So we want to calculate the volume of this cube. Of course, the reason why it is a cube is that all the edges are equal. So we are going to apply the formula. V is equal to L cubed. And therefore, we substitute. And 6 cubed is 216 meters cubed. That is the volume of that cube. We are just using reminders because these are things we have done in year 8. And therefore, we are just reminding ourselves on what we had done earlier. So you can see these are the two basic formulae that we can use. And the same application can be done in other objects, like other prisms, for example, cylinders. Let's look at the volume of a cylinder. How do we calculate the volume of a cylinder? We start from that premise that volume is equal to length times width times height. That is the premise we start from. But remember, when we have for our cuboid, we had length we had width. So you can appreciate that from this particular basic formula for calculating the volume of an object. We have length times W, and our W is the width, our L is the length. So we have V is equal to length times W times height. This part here, this part, the part defined by length times width, is basically known as base area. It is the base area. Then we multiply base area by height, we get volume. So in the same notation, on the same notation, we can now see that if length times W is base area, and the base area of a cylinder is circular, the base area of a cylinder is circular, it therefore implies that for circular bases, area is equal to pi r squared. Because it is a circle, so we get area is equal to pi r squared. So, because it is base area, we can therefore see that length times W for a circle, equals to pi r squared. So we can now easily substitute where there is length times width, we substitute with pi r squared to obtain the volume of a cylinder. So because this defines base area, and our base area is circular, and therefore is defined by pi r squared. So it implies that for a cylinder, volume is equal to pi r squared, and therefore we are now able to calculate the volume of any cylinder if given the dimensions. So for this cylinder, we have radius as 3.5 meters and height as 10 meters. So we can calculate the volume. We get 3.5 times 3.5. 22/7 times 3.5 times 3.5 times 10 as the volume. So upon simplification, so we get volume as 385. Volume is 385 meters cubed. So for a cylinder, the first important thing that you must appreciate is to calculate the volume we write the formula pi r squared h. And therefore, once you have that, you are now able to substitute any dimensions given in this formula, and you work out the volume quite easily. So class, what guides us in the calculation in volume of prisms is the type of the base we have. We must first of all get the base area, and after we have gotten the base area, we can now be able to calculate the volume of that object without much problems. For example, if even we have a cone, the base is circular, and the curved surface is also circular. But remember, this is a cone, it is removed from a particular cylinder. So we are able to calculate base area times height to give us the volume of any particular object we have in life. So let's look at exercises on various prisms. So we have further prisms. So for a cone, we have volume is equal to 1/3. This formula is derivative, can be derived, but for this purpose, at this level, we state the formula. A third pi r squared h is a third of h multiplied by the base area. You can see pi r squared is the base area multiplied by a third h. That will give us the volume of any cone. So if we have an example, so we have the radius as 2.1 meters, but the height is 4 meters. So by the use of the formula a third pi r squared h, we are able to substitute for these values in this formula to determine the volume of that cone. So we get the volume as 22 times 0.1 times 2.1 times 4. Let's see what the answer gives us by our calculators. So you get 18.48 meters cubed. So easily again, we have found the volume of a cone by stating the formula and working out the numerical values on the examples we have been given. So once you know the formula, then you can easily substitute your values in that formula and get the numerical values of the volume of any particular prism. So we move on. Let's move on and see other objects. Now let's look at frustums. Now class a frustums these are three-dimensional objects that are generated from other prisms. For example, if we have a cone and cut it, we'll have what we call a frustum. And for that case, we can now use the application of various volumes to determine the volume of that particular frustum. I want to give an example of a circular-based frustum. This is the original cone which we want to make a frustum from. So we assume that we cut the top part. So when we chop off the top part, this is what we obtain. That is what we obtain. So this is the figure we are calling a frustum. So the top radius is small, we call it r small. The base radius is big, we call it r capital. And the frustum are always shapes or objects that we make. We generate a shape. For example, if you have drinking glass, it is made in the form of a frustum. And therefore, we can calculate the volume of that particular frustum by just applying the formula that we have. We want to look at what we will have there. So the smaller cone, I want to name it The smaller cone has a base radius of r, so it is made of B, C, D, and the bigger cone is O, A, D. So we remove the small part of the, we remove a smaller cone from the bigger cone. So when we chop it off, we get this particular kind of object. And this is now what we call a frustum, whose volume now can be a function of the two small cones. You say this is H. And from the top to the bottom, we call it capital H. So capital H is equal to length OD. From O to D is capital H. From C to D, we call it small h. H capital is OD, H small is CD. So from this particular information, to get the volume of a frustum, we first of all get the volume of the bigger cone, then we get the volume of the smaller cone, we subtract the two. When we get the difference between the two, we get the volume of the frustum. So let's see how we move on with that. So volume of the bigger cone is given by a third pi r squared h, because the base radius is capital H. And the volume of the smaller cone V2 is given by a third pi r squared small h, as we had already defined. So from these two particular volumes, we are now able to calculate the volume of the frustum. So volume of the frustum V is equal to V1 minus V2, where V1 is the volume of the bigger cone, V2 is the volume of the smaller cone. So where there is V1, we substitute with this, and where there is V2, we substitute with that. So let's see. That is the volume of the frustum as a function of the volume of the bigger cone minus the volume of the smaller cone. That is the volume of the frustum. So once we know that, we can now be able to substitute for those values in a particular equation given, and we calculate the volume of the frustum. Mathematically, we are also allowed to do factorization, but the most simple only will be, first of all, to work out this. You can work out this independently. You work out that independently, then you do the final subtraction, which will be very, very easy. So let's look at an example. So this is the frustum. We have been told to find its volume. We have been told that it is made from a cone whose base radius is 2.8 meters and a perpendicular height of 6.3 meters. So using that information class, we can find the volume by first of all finding the dimensions of the smaller cone. We find the dimensions of the smaller cone. This is how it looks like after removal. So this is OABC. So the radius BC is 1.4. The radius OA is 2.8. This height, we call it H, which we don't know. Neither do we know this, but we know the 2 radii. So what we do is we use what is called correlation. From the unit 8 we did linear scale factor, and we say that linear scale factor is just a linear relationship between 2 dimensions. So because this is radius and that is radius, we can calculate the linear scale factor in correspondence to this particular height, because this height is H is equal to 6.3 meters. H and H are also correlated. So using linear scale factor, we can find this small h because we know capital H. But how do we get that? We say that the ratio of the radii is equal to the ratio of the heights. So by use of we obtain R over R should be equal to H over H capital. R small over R capital should be equal to H small over H capital. And because we know R small is 1.4, R capital is 2.8, H capital is 6.3, we can calculate H small. So let's do the basic substitution and obtain that. H over 6.3 is equal to 1.4 over 2.8, which further implies on simplification we get is equal to a half, so that we get our H we get 3.15 meters as our small h. Now that we have gotten our small h, we are now reset to calculate the volume of the frustum. By using the formula we've learned, let's now get the volume of the bigger cone. We get the volume of the smaller cone, we subtract, and that will be the volume of our frustum. So we move on. Volume of the bigger cone is a third pi r squared h. Then because we know r, we know capital H, we substitute. Sorry. A third times 22 over 7 times 2.8 times 2.8 times 6.3. Upon simplification, let's see what we obtain. Using our calculators. Can we use our calculators to work out this? And then let's confirm our answer. If you confirm, what do you get? So you should be able to get 51.744. That is the volume of the bigger cone, the original cone. Now let's get the volume of the cone that was chopped from the bigger cone, and we call it volume of the smaller cone. A third times 22 over 7 times 1.4 times 1.4 times 3.14. When you simplify that, by our calculators, when we multiply, you should be able to obtain V2 as 6.468 meters cubed. So we have the two volumes of the two cones, but we want the volume of this, and therefore so we have 51.744 minus 6.468. We obtain, when you subtract the two, you get 45.28 correct to 2 decimal points. You'll be able to obtain 45.28 meters cubed, correct to 2 decimal points. That is our volume of the frustum. So you can see, once you know the volume of the cone, you can get the volume of any frustum from the calculation, the basic calculations of various volumes. So let's move on to the next figure, that is frustum. We can also have square-based frustums, use the same formula. We have rectangular-based frustums, we use the same formula. Let's move on. For a spherical object, we know that a spherical object is a homogeneous object. That means it has uniform dimensions and it has a radius. So to get the volume of a sphere, we have V is equal to 4 over 3 pi r cubed. That is how we get the volume of a sphere. And once we state this volume formula, we can now calculate the volume of any sphere given the radius. So let's look at an example. So the radius of this sphere is 7 centimeters. So basically we have 4 over 3 times 22 over 7 times 7 times 7 times 7. That will be the volume of that sphere. And once we simplify, when we simplify, we obtain, using your calculator, when you use our calculator, you get 1,000 1,437.33 centimeters cubed. That is the volume of a sphere. So once we state the formula, we are now able to substitute and get the correct answer in the questions that we are asked. Finally, class, volumes of composite objects. Now, when we talk about composite objects, we basically mean that these objects are made from different other basic objects. For example, we can have a semi-cylinder being combined with a cone. We can have a semi-sphere being combined with a cuboid. We can have a frustum being combined with, let's say, a cube. So those are what we call composite objects. So let's look at examples. So this is a composite figure. You can see it is made of two basic objects, the conical part and the cylindrical part. So you can see the dimensions of the object are indicated, but because this is a cylindrical part, we first of all find the volume of this cylinder, and this is a conical part, we find the volume of the cone, and then we add the two, and that will be the volume of the composite object. So let's start. Volume of the cylindrical part is given by pi r squared h. Upon substitution, we get 22/7. And that gives us 385 meters cubed as the volume of the cylindrical part. Then we get the volume of the conical part. One over 3 pi r squared h. You do the substitution. Times 5.6. We simplify. So when we simplify, we obtain by your calculators you obtain 7.19 meters cubed. So because the object is made of two basic objects, we now add the two volumes. V1 plus V2. You get 392.19 meters cubed as the volume of this particular composite object. And we look at more examples on that in our next class. More examples on composite objects in our next class. Otherwise, that marks the end of the lesson today. Have a good morning.